Today, we're learning about Newton's laws of motion. Let's start with the first law of motion, also known as the law of inertia. It states, an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity, unless acted upon by a net external force. Let's understand this with a simple example. Imagine a box with a mass of 10 kilograms resting on the ground. First, gravity pulls the box downward with a force called weight. We calculate it like this. Weight equals mass times gravity equals 10 kilograms times 9.8 meters per second squared equals 98 newtons. This is the force with which the Earth pulls the box down, but the box isn't sinking into the ground. Why? Because the ground pushes upward with an equal force, called the normal force, also 98 newtons, but upward. These two forces, gravity and the normal force, are equal in magnitude and opposite in direction. They cancel each other out, so the net force is zero, and the box remains at rest. This is exactly what Newton's first law describes. Now, let's say you push the box with a horizontal force of 20 newtons. There's no longer a balance. Now there's a net force to the right, and the box starts to move. Once it's moving, it wants to keep moving forever at the same speed and direction. But in the real world, friction gets in the way. Let's say the force of friction is 5 newtons, acting to the left. While you're pushing with 20 newtons, and friction resists with 5 newtons, the net force is 15 newtons to the right, so the box accelerates. But if you stop pushing, friction is the only force left. Now, the net force is 5 newtons to the left, and the box slows down. Eventually, it comes to a stop. So to summarize, the box stays still because gravity and the normal force are balanced. It moves when an unbalanced horizontal force is applied, and it stops due to friction, which is also an external force. That's Newton's first law of motion. It tells us that objects resist changes in motion unless something forces them to change. Now, let's move on to Newton's second law of motion. This law explains how an object moves when a force is applied. It says, the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Or, in formula form, F equals m times a, where F is the net force, m is the mass, a is the acceleration. Let's use our same example, a 10-kilogram box on a flat surface. Imagine you push it with a net force of 30 newtons to the right. Using the formula F equals m times a, we can solve for acceleration. A equals F divided by m equals 30 newtons divided by 10 kilograms equals 3 meters per second squared. That means the box will speed up at a rate of 3 meters per second squared as long as the force continues. This acceleration is in the direction of the force, so the box moves right and gets faster every second. But remember, the surface the box is on may have friction. Let's say friction pushes back with 10 newtons. You're still applying 30 newtons, so the net force is 30N push minus 10N friction equals 20N net force. Now, the new acceleration is A equals 20N divided by 10 kilograms equals 2 meters per second squared. The box still speeds up, but a little slower than before. And what if friction equals the pushing force? If you push with 10 newtons, and friction also pushes back with 10 newtons, then net force equals 0. Acceleration equals 0. The box moves at a constant velocity, or stays still if it wasn't moving. So Newton's second law tells us more force, more acceleration, more mass. less acceleration for the same force. If no net force, no acceleration, it's a powerful way to predict motion. All it takes is mass, force, and a little math. Now let's talk about Newton's third law of motion. It says, for every action, there is an equal and opposite reaction. That means forces always happen in pairs. If one object applies a force on another, that second object pushes back with the same amount of force in the opposite direction. Earlier, in Newton's first law, we explained why the 10-kilogram box doesn't fall through the floor. The normal force pushes up with the same strength as gravity pulls down. That was already an example of two opposite forces in balance. But now, let's take a different and simpler example. Picture two identical cubes touching each other on a flat surface. You push cube A to the right, so it bumps into cube B. As A pushes B, action, cube A applies force on cube B. Reaction, cube B applies equal and opposite force on cube A. If there's no friction, cube A slows down, and cube B starts moving. Even though the shapes are simple, the forces between them follow Newton's third law perfectly. So remember, all forces come in action-reaction pairs. The forces are equal in size, opposite in direction, and they act on different objects. Whether it's a box, a ball, or a cube, Newton's third law is always at work, quietly making sure every push gets pushed right back.